Welcome to this rather theoretical start of the course. But it is needed. So we will need linear algebra during the lecture quite a lot. In fact, I always see, or I would also describe data mining and machine learning as a discipline which is a combination of statistics and optimization theory and linear algebra mostly. And then of course you have to learn also the programming. But yeah, these are all the tools that we need, and linear algebra is one skill set, so to say, which is required in order to do stuff in data mining and machine learning, or to even understand how to implement things fast and how to understand why something is the way it is. Now, if you did not have linear algebra before, then this might feel like a lot to take in. And that is just so, but this lecture will be everything you need for the whole course in terms of linear algebra. So it's not really necessary for you to understand now everything in one go and to remember everything, but just take into account that if you have struggles later with understanding some of the concepts we need in the lecture, that you can always go back to this lecture and then look it up. So it's not like that you really have to understand everything now. We will rehearse the stuff in the lecture, but you should be aware of the material which is covered here, and maybe you can also put your hands on some of the calculations to understand how stuff works. Okay, so I say how stuff works. What stuff? Yeah, the stuff is mostly the stuff which is happening in vector spaces. So the definition of a vector space is rather boring and long, but I think it's quite important to remember what it's actually saying. So a vector space over the real numbers is a set of vectors with two operations, the plus and the scalar multiplication, such that the following properties hold. Now, first of all, the addition is like we know it from normal numbers, from real valued numbers. So for any two vectors, v and w, we have v plus w is again a vector. So for example, the vector z. And it's an abelian group. So that means that v has an inverse. And if I add now on both sides minus v, then I have there standing now minus v plus w is equal to z. And now minus v is the inverse of v with respect to addition, and minus v plus v is 0. So we get w is equal to z minus v. For the scalar multiplication, we have now one scaling factor alpha and one vector v, and then the scaled vector alpha v is also again a vector. This is what the definition says, and the following properties must hold. So the first one is the associativity of the scalar multiplications. If you concatenate scales, then it doesn't matter in which order you do it. That is what this says. And also you have a one element, so if you multiply a vector with 1, if you scale it with 1, then you get the vector. That is basically what it's saying, and this also makes sense, right? And you have a distributivity, so plus and scaling is working together as we are used to it by the distributivity law, and this means that you can basically multiply out the product from a vector times the scaling factor alpha plus beta, and the same you can do with the scaling of a vector which is itself an addition of two vectors. Okay, so this is what we can do. You see already that you can do most operations from real numbers. Like for example with plus, it behaves very much like what you know from real numbers. But not everything goes now. So what you cannot do is, for example, multiply vectors. This is not defined here generally in a vector space. And you cannot divide by a vector, which is also, which makes sense. If you cannot multiply with a vector, then you can also not divide. And which vector space could you actually know? So the most familiar vector spaces, or the most common ones, is the space R to the power of D. This space is a space of d-dimensional vectors. So the vector v here has d components, and they are written over each other vertically. The addition between vectors and the scaling is then defined as follows. So we have the addition of two vectors, v plus w, is just performed element-wise, and the scaling as well. So it's just like element-wise addition and scaling for this vector space. And what does it show? So what does it look like in a space when we apply these operations? So for example, the vector space R to the power of 2 can be visualized here in 2 dimensions. So the first one is here, this is the axis x1, and this is the axis x2. And then every vector has, like here, basically this is 0.5, for example, for v is x1. And this is x2, 1.5 for v. So we have here now our vector v, which is the red one here, and we have our vector w, which is the green one. And when we now add these vectors, so v plus w, then it is basically like I follow the vector of v, and then I just start here at the end of v, and then I go along as if I just put the vector w, like if I concatenate the vector w from the starting point at the end of v. And this is then the vector v plus w. Yeah, the scaling just basically takes the vector, but the length is then multiplied. So this is the length here of v, and this is the length here of v, and then we have here 2 times v. Okay, so this is what it looks like to scale and to add a vector. Now, is there something else which might be important next to what we probably already know, like the vector space of R to the power of D? Yes, very much so. And this is the vector space of matrices. Okay, why are matrices important? Matrices are important because we are here in data mining, and data is represented as a matrix. So for example, here you see just a tabular description of a matrix, or a tabular representation. And we have here the features f1, f2, and so on until fd. So we have d features, and we have n observations. And now every observation is here 1 row. And you can also see this as a n times d matrix. Okay, an n times d matrix. What is this? An n times d matrix concatenates n d-dimensional vectors column-wise. And then a dot j denotes the column vector j of a. So, okay, what does that mean? The column-wise representation of a matrix is given like this. So we have here the matrix A, and then we have here d concatenated columns, and this is the vector a dot 1 until a dot d, and these are the column vectors. So this means basically where the dot is, we let our index 1 from 1 to n here. Like this is the first column, and this is the last column. But we do not have to see this as a concatenation of columns. We can also just see a matrix as a concatenation of rows. The dimension of a matrix is like the first number n here is the number of rows, and the second number d is the number of columns. Okay, so if we say that these matrices are a vector space, how can we define our operations plus and the scaling actually? And just like with vectors, we do this element-wise. So for every element, we just apply the the plus we know. And here every element is scaled with the factor alpha. Okay, now with matrices we can, more things are interesting than, for example, just with real numbers. And one of those things which are interesting is, or different, is the transpose. So the transpose is basically just the operation to swap the dimensionality of a matrix. And that means basically that it changes row vector into column vectors and vice versa. For example, we have here the matrix A, and the matrix A is in R to the power n times d, so it's an n times d matrix. If we then apply the transposed, then every column vector here becomes now a row vector. So the first column vector is now the first row vector, and the vector is transposed. Or how you can also see it, basically what you do is you fix here the diagonal. You see here that A11 until AND is the same. And then you have to mirror the elements to the diagonal. For example, this value here, A1D, gets now here, and this value AN1 becomes the top right element. And you see here, so what has before been an n times d matrix is now a d times n matrix. And I've already said that that here we have the transpose, which makes of the first column vector here row vector. So the transpose of a vector, what does it mean? It's basically that you interpret now a vector as a d times 1 matrix, d times 1 dimensional matrix, and then the matrix which is defined like this is in the transposed version is basically lying down. So the vector in its normal notation is upstanding, and then the transpose is just lying down. And what kind of properties do we have? So one of the very easily pertained results is that the transpose of the transpose basically does nothing. So how is that? Why is that? So here we have the matrix A, and if we make the transpose, then the first row becomes the first column. So we have here 1, 2, 3, and here is also 1, 2, 3. And the second row becomes the second column. And then we do the same with A transpose. Now we transpose it again, and now the first row becomes again the first column, and the second row the second column, and the third column the third row the third column. And then you see that basically you have again the same matrix. Which just makes kind of sense, because if you mirror 2 times, then you get again the original picture, right? And we said that transpose is an array can be interpreted as mirroring on the diagonal. One special type of matrices are symmetric matrices, and those are the matrices which are invariant to transposition. So a matrix which is symmetric has to be quadratic. So here the number of columns is the same like the number of rows, 3. The diagonal doesn't get changed by transposing it, so this doesn't matter. But what the structure of a symmetric matrix is that you see that here on the opposite of the diagonal, basically they are the same numbers always. It's a perfect mirror picture of the upper triangle. Here this is the upper triangle, and the upper triangle is mirrored here into the lower triangle. So one special matrix is the diagonal matrix, and this is a symmetric matrix which has only non-zero elements on the diagonal. And we denote this as this, so the diagonal matrix, which is basically induced by the elements A1 until AN, is a matrix which looks like this. So the elements here in the argument are denoted as the diagonal, and everything else is 0. And of course it's symmetric, because if you mirror here the zeros, then yeah, they become 0, right? Okay, great. We can add, scale and transpose matrices or data. Isn't that kind of lame? Yes, but it gets more interesting with the matrix product. But we will just have a look at this in the second part, so click on the next video if you're ready for it.